let's take a look at the Doppler effect. So the Doppler effect is the description or explanation of how waves are altered, either by having a moving source of waves or by having a moving observer of the waves. And its impact, its influence, will be different based on whether you're talking about mechanical waves or electromagnetic waves. Remember, mechanical waves are waves which cause oscillations in a medium, so like sound waves and water waves. Electromagnetic waves are a different category. They don't require a medium, so they're kind of a special category. So consequently, we're going to talk about the Doppler effect in kind of three different ways. It's three different descriptions. We're going to have one description of the Doppler effect for when you have mechanical waves and a moving source. Another description of the Doppler effect for when we have mechanical waves and a moving observer. And then a third description for when we're talking about electromagnetic waves. And that third description of electromagnetic waves, it applies whether or not you have a moving source or a moving observer. So first let's think about mechanical waves with a moving source. So if the source is moving, then the wave fronts in front of the source will be closer together, and the wave fronts behind the source will be further apart. And I'll try to draw a diagram or a little picture of what I mean by this. So here we have the moving source, and as it moves, it emits these wave fronts. And the wave fronts bunch together in front of the source. Now imagine we have an observer over here. When the waves reach the observer, the ones in front of the source are going to be closer together. The wave fronts are closer together, and so those waves will have a smaller wavelength and a higher frequency. Once the source moves past the observer, the wave fronts are further apart, or the wave fronts reaching the observer are further apart, and so we'll have a larger wavelength and a smaller frequency. And the equation which describes this is right here. F prime equals F times V over V plus or minus US. V prime refers to the frequency observed by the observer. F refers to the frequency of the waves which are emitted by the source. V refers to the wave speed in the medium. And US is the speed of the source. Now this plus or minus, you got to figure out whether or not you use the plus or the minus based on the situation. So let's think about that. If the source is moving toward you, you would expect to get a higher frequency. Well, let's see. To get a higher frequency, we would want the denominator over here to be smaller. In order to get a smaller denominator, we'd have to use the minus sign. So the minus sign is used when the source is moving toward the observer. If the source is moving away from the observer, then you'd expect to get a lower frequency, a smaller frequency. And to get a smaller frequency, you'd want a larger denominator, and so you use the plus sign. So the plus sign is used when the source moves away from the observer. Okay, now let's think about if we have mechanical waves and a moving observer. So the source doesn't move now. The source is emitting these wave fronts, and they go out like this. But the observer is now moving toward the source. If the observer moves toward the source, it will encounter the wave fronts more rapidly than if it was just standing still. If it encounters the wave fronts more rapidly, that means it receives a higher frequency, or it observes a higher frequency. And if it was on the other side, and if it was moving away from the source, then we would expect it to receive a lower frequency, right? Those wave fronts are going to have to try to catch up with the observer, and so the wave fronts won't interact or won't reach the observer quite as often, so you get a lower frequency. So this is the equation that describes that situation. F prime is equal to F times V plus or minus UO over V. Here, F prime, again, is the frequency observed by the observer. F is the frequency emitted by the source. V is the wave speed in the medium. And UO is the speed of the observer. So let's think about this, the plus or minus. Which one do we use when? Well, if you're moving toward the source, you would expect to get a higher frequency. To get a higher frequency, you'd use the plus sign. So you use the plus sign here when you're moving toward the source. You use the minus sign when you're moving away from the source, because that will give you a lower frequency. All right, now let's talk about electromagnetic waves. Electromagnetic waves are a different category because of the special theory of relativity, or the theory of special relativity, excuse me. This theory of special relativity requires that the speed of light is the same for all observers, whether they are moving or not. We're not going to get into this. This is a whole other can of worms in physics, which we're not going to really get into right now. But the ultimate point is that electromagnetic waves behave differently on a fundamental level, and so those previous equations for the Doppler effect don't apply anymore. Instead, we have this expression. Delta F over F is equal to delta lambda over lambda, which is approximately equal to V over C. So delta F is the change in the frequency. F is the original frequency that was emitted by the source. Delta lambda is the change in the wavelength. Lambda is the wavelength of the wave emitted by the source. V is the speed of the observer or the source, whichever one is moving, and C is the speed of light. Now, the trick with this equation is that you have to determine whether the delta F or delta lambda is going to increase or decrease the original frequency or wavelength. If the observer and the source are getting closer together, if they're moving toward each other, then the frequency has to get bigger and the wavelength has to get smaller. So you take whatever that delta lambda or delta frequency is, and you would cause the frequency to get bigger or the wavelength to get smaller. If the observer and the source are moving apart from each other, then you'd expect the frequency to decrease and the wavelength to increase. So you'd take that delta F and get a smaller frequency, and you take that delta lambda to get yourself a larger wavelength.